Hi, I'm Alex Garcia, and thanks for joining us here at NTWC Live. It is a team effort between Bill Reed, Tim Smith, and I. We'd like to say thank you to a few groups that helped make this possible. It's USAA, South Padre Island Convention and Tourist Bureau, the Weather Company, and the Weather Boy. And now, here's Tim Smith.
Good morning, everybody. Welcome to NTWC Live for Wednesday, July the 13th. It's good to have you all along today on this hot day in South Texas. Not everybody on this call is where it's so hot, so we'll get to some cooler weather in just a moment. Alex thanked our sponsors, but we want to mention them again because without them, this program wouldn't be a possibility. USAA, thank you for what you do to make these programs a possibility. We couldn't do it without you, so USAA, thank you so very much. The South Padre Island Convention and Visitors Bureau. We meet every April on South Padre Island, and they're wonderful hosts. And we always have a nice time there at the Marriott Courtyard on South Padre Island. We invite you to join us next April. We'll be there live again. We also thank the Weather Company, Weather Boy, the City of Brownsville, the Port of Brownsville, Black Magic Design, Walmart, all folks who are part of this program day in and day out, and we appreciate all of that. Bill Reed, Hal Needham are both with us, and our speaker, of course, with us today as well, Derrick Herndon. We'll get to them in a second. I do want to before we get going, I want to show you something that I was able to see last week. You know, we talk about different kinds of tropical weather, and let's go back up here to the top. And there you see where I was last week. I was in Cabo San Lucas, the very southern tip of the Baja Peninsula there. And I'm going to put this in the play mode. It loses all its animations. I'm kind of disappointed that it doesn't animate, but you'll get the idea. And where we stay is literally on the very, very, very southern tip of the Baja Peninsula. It's called Land's End, and we're facing due south. And so that's kind of looking off to the southeast from where we are. And I can play some sound for you, even though you don't see the movie running. That's what it sounds like. And the next landmass looking straight south is Antarctica. So there's a lot of Pacific Ocean out there. My eyes, even from the fifth floor, weren't good enough to see that. But about 400 miles offshore was Hurricane Bonnie while we were there. And that cloud that you see on the left is all we saw of it atmospherically. But on the sand, we saw a real significant impact. So I want to start with this picture right here. That's looking to the left out of our hotel room, obviously, looking down at Land's End. To the right is straight south. Bonnie went by to the right by about 400 miles. And we're going to focus on that area in the box right there, okay? And there's one lone rock kind of out on the right there, a little tiny rock. Let's go a little closer. But then you see more rocks off on the left. I'm going to focus on that rock, okay? And this is on Sunday, July the 3rd. That was our first full day there, okay? Well, Bonnie went by 400 miles to the south, and that same rock is the one that's right in the middle of the picture right there. They went from, that's the same rock on the right side of the picture there. And behind it are all the big rocks, the big Land's End down there. But when we were there, this was on the July 10th after the storm had gone by. All of that area around that rock and way off to the right was beach, and it was about probably 50 yards of beach. And this is the day after the storm, and there was they won't let you get anywhere near the surf out there. There's a guy standing there just keeping you away from it. But all of these rocks right here 4 days earlier had been covered in sand. This little rock just stuck up maybe about 3 feet, and now that's about 8 feet tall. So about 8 feet of sand got washed out in here. And the guy told us that we should take a good look at these rocks, because by next year at this time, they'll be covered again. No matter what happens, they'll be covered again. So again, we're looking at that rock right there. That's the one that we're looking at in that picture. So that water this was where it was Sunday. The water was all the way up to that blue arrow on Thursday, and a lot of that sand had been washed away. Pretty remarkable, I think, but the hurricane was 400 miles that way. On our last day there, I'm trying to figure out who that was up there. I figured that must have been Hal.
You caught me.
We weren't sure where you were, but we figured that was you up on top of the rock up there. So, but I thought it was interesting, just the impact of a storm that was, 400 miles away. You can really see it. really see it. So, Hal, I know that wasn't you. It just looked like you up there fishing.
It actually looks like Obi-Wan Kenobi with a fishing pole, or maybe the magic wand. I don't know.
half the line is half the spool would be to get to the water from there. So,
and we never saw him bring a fish up the whole time he was up there. And then some pretty good grip shoes because that's on a pretty good slope. So anyway, that was last week in Cabo with Bonnie going by to the south. Bill, there's stuff going on in the tropics now today, aren't there?
Yeah, we're into the second official month of the season now, so we get stuff going. I had a quick question on do they replenish the sand there, or does it naturally reaccrete?
They told us that it naturally shows up again. We were there after Hurricane Odile back in 2014. We were there the next summer, and there was no beach, and they were in the process of replenishing. But they said this normal process, it will replace itself, and by barring any other big hurricanes, which you'll talk about in a minute here, but barring any other storms, it will replenish itself over the course of the next year, and a lot of those rocks will be covered up again. And we've seen it come and go. We've gone several times, and we've seen varying degrees of visibility of those rocks.
Yeah, so many of our beaches it's constantly losing. So when you have a big event like that, it just accelerates the loss.
Yes.
Okay.
Okay. Tropical update. Bill, take it away.
All right. Let me see if I get to the right place here this time. Why, hi, I did. Can you see the picture? I forgot the text earlier. Good. Okay, we'll start with Atlantic outlook. If you recall, all week we've been monitoring a system tucked into the northern Gulf Coast that Ntwc had a low chance of it developing. I think the highest they had out was day before yesterday, a 30% chance. And they had the right wording in there. It had to get farther away from land to have any reasonable chance to develop. Looked like a pretty nice little swirl going on that came inland in the Florida Panhandle yesterday, but today it's all a shear line with the convection there, and the conditions don't favor development, and it's now a 0% chance. The big picture of the tropical Atlantic, the most remarkable thing on it is the large quantities of dust that are advecting westward across in the trade winds now. Through most of the Caribbean. Looks like there may be a little active wave down here, but neither the models nor Ntwc talk at all about it developing in any way, shape, or form. So it looks like we're going back into the quiet mode unless we get something funky going in the Gulf again, that like we just had this last week. A little close up on that. There is a lot of convection down there. Normally at this time of year you see that, and Tim and I get into the beads of sweat mode, and Hal gets to be drooling happily about something happening, but it's pretty much the upper shear zone triggering that, and the mostly anticyclonic flow down in there now, weak flow as it is, and the pressures are starting to come back up. We'll see. Worth keeping an eye on. Shifting gears, we're in the Pacific season, of course. There's Darby. I'll talk about it in a moment. The next system in line for the Eastern Pacific looks, the probabilities have been jacked up now to 30% in the next 2 days, 80% in 5 days. It's almost on the same trajectory that Darby was initially, and it's forecast to develop rather significantly from this weekend and beyond, and track well offshore of Mexico and the Pacific Ocean, and maybe get another high surf event going on in the Baja. If it holds up long enough, maybe the surfers in Southern California will enjoy a little bit of action with that. There's a satellite image. This is the system south of Guatemala that they're monitoring for development. Currently, you don't have a low, but it's the area that's most favorable. The models are pretty happy with it. The funny thing happened overnight. It looked, the eye filled up with clouds, and it was following the forecast real nicely about a steady to even rapid weakening trend. And then right after the forecast went out at 9Z, eye pops open again, so they've had to jack the winds back up to 105 miles an hour. It's on a westward trajectory, heading towards open Pacific, and colder water and dry air and shear. All that combined says that by by Friday, we should have dwindled down to a remnant low over the Pacific southeast of Hawaii. That's all the things I have on the tab. So I guess that's all I was going to chat about on the current weather there. Okay, to our program today, we're privileged to have as our guest Derrick Herndon. He's an associate researcher with the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin. He started working there 20 years ago, and prior to that, we had a shared common experience. He had an 8-year tour with the U.S. Navy, which pointed him, I guess, in the direction of meteorology. And I see you have your bachelor's degree from Florida State University, a well-known place for gaining tropical knowledge. So welcome, Derrick. Tell us a little bit about your work.
Thank you, Bill. Appreciate it. So yeah, actually, my interest in meteorology predated the Navy. I grew up in Florida, so
Okay.
lots of tropical activity there. So I kind of garnered an interest in meteorology and specifically in hurricanes, just growing up in the Miami, then the Tampa area. Yeah. So my interest obviously was meteorology from a very young age. I actually can kind of date it back to like when I was about 7, seeing a water spout in the Florida Keys. So I always had this interest and wanted to do something with it. Didn't have a lot of money. The Navy offered me a really good opportunity. They said, "Hey, you just do a little time with us and we'll send you to school." So it was a really good deal. I was able to use the GI Bill to kind of pay for my college at that time. So I actually will say that, from a perspective of going to school and meteorology, having forecasting experience going in was super helpful. So, a lot of people were struggling in their synoptic meteorology classes, but I was flying through all that because I had already been doing that for close to 8 years. So, I did some time in the Navy. I was a forecaster, got to work on a number of different ships, a number of different environments. Very challenging to forecast at sea. We had a lot of tools. We had some satellite data. We had some model data, but not nearly as much as folks have now. It's pretty phenomenal what forecasters have access to these days, even out at sea, compared to what we had even 20-something years ago or so. So, my interest was meteorology, hurricanes, and out of the Navy, I did a little work. After school, I did some work at a private company called Whirlwinds down in Mississippi there. And from there, I went to here where I'm at now in Madison at the Cooperative Institute at the University of Wisconsin here, where, we actually, whenever I talk to people about what I do and I say I study hurricanes in Wisconsin, the very first thing they say is, well, there are no hurricanes in Wisconsin. And so the answer to that is that, this university and specifically the Space Science and Engineering Center has a very, very rich heritage of working with satellite data. And almost all of the work, that we do for analyzing hurricanes, especially outside of the Atlantic, is using satellite data. So it was a really good fit for me to come here and do this work. The work that I do is to use satellite data to analyze tropical cyclones worldwide. And when I say analyze them, there are a couple of things we need to know. We need to know, number one, where is the storm located? What's its center position? Because that's really key. And also, how strong is it? And as I mentioned, like 80% of the storms that we analyze on the planet here are analyzed with satellite data. So that's what I do pretty much day in and day out is processing satellite data to try and give forecasters a better sense of where the storm is located and how strong it is. And it's some of our more recent work has also kind of moving beyond just the current intensity to try and understand how far out the winds extend and also the structure of the storm, because the storm structure, anyone who's ever seen hurricanes or followed hurricanes for a little bit of time knows that they come in different sizes and different shapes. And those different sizes, shapes, structures can definitely impact how the storm will change over time. So we're trying to get a better handle on some tools to give to the forecasters to understand when these storms will undergo those structure changes.
Yeah, that's like you said, it's just amazing how different it's become in that regard. My first introduction to using satellites with tropical cyclones was the development of the Dvorak technique. I even was privileged to sit in on a seminar that Dr. Dvorak himself presented back in the 70s when I was first starting out in the Weather Service. So we still use that, but I have a feeling we do it a lot differently now with the satellite imagery we have than we used to. Can you educate us a little bit on where we are with that and where we might be going?
Right, so that's a really good point. So this Dvorak technique is a technique that looks at geostationary satellite imagery. Primarily, they use the infrared channels. So we're looking at the cloud top temperatures. And surprisingly, it really hasn't changed a whole lot since the early 80s when it was kind of updated to include the infrared component, and some tweaks were made at that time. It's somewhat unchanged. There are a couple little tweaks that have happened over the years. For example, the way we use it in the Atlantic might be slightly different than how they do it out in Japan and the Western Pacific, and the Bureau of Meteorology in Australia has some changes that they do, primarily because the troposphere is higher out there and they have colder cloud tops in those satellite images, and they have to kind of make some adjustments to account for that. But the technique itself, I mean, fundamentally is fairly unchanged, and it's really remarkable that Vern Dvorak came up with this method. I'm not sure he really would have thought that this would still be being used in 2022, right? He would have probably said, no, we'll move well beyond that. And in many ways we have a lot more tools now. We have we have better satellites. We have microwave satellites now, scatterometers, synthetic aperture radar, lots of other tools. But the heart of position and intensity analysis still is pretty anchored in the Dvorak technique. Every warning agency that does tropical cyclone analysis uses it. Either they use someone else's estimates or they do their own. One thing we do know, though, is that there is a subjective component to this technique. You know, when the features are really obvious, like when you have a very clear eye in the hurricane, it's a much more objective type technique. It's very easy to find the center. It's much easier to get the intensity from the flow chart that people use to do it. And I could show an example of the flow chart if anyone wants to see it. It's anybody.
Good idea just to see how rigorous it really is. If you got one handy.
Sure, I'll pull it up. So we just actually did a training course for the American Meteorological Society a few weeks ago, and we actually did an exercise. So we had some students who chimed in and sat in on this course, and I actually had them do this. I actually had them do a Dvorak estimate, and anybody can do this. Anybody could follow this chart, and if they have the imagery available to them, they can estimate the position and the intensity of a tropical cyclone. But it takes years really to get good at this. It's fairly straightforward if you just follow the flow, but there are a number of quirks in the technique, and really the hardest part about this is remembering some rules. And Vern was pretty smart when he realized that sometimes tropical cyclones, their structure, the temperature of the clouds may fluctuate on order of 6 or 12 hours or whatever, and some of that's a diurnal fluctuation in the storm. And he recognized pretty quickly that those fluctuations didn't really result in changes in the intensity. So there are rules to prevent you from changing the intensity too much, too fast with this technique. And it was pretty smart of him to do that. There are times, however, when the storm will be rapidly intensifying so fast that you can get a little bit behind on this technique. So this is what the flow chart looks like. So this is the enhanced infrared analysis diagram. The flow chart for the Dvorak technique, pretty much about as it existed. This particular chart was created by the Bureau of Meteorology with some slight changes to it. But I'm just showing this as an example here. So you can kind of see that you have this kind of pathway where you start. The very first part of the process of tropical cyclone analysis is where is the center? It's really key for this technique because the location of the center relative to where the thunderstorms are located is very important for getting the right answer as far as the intensity. So you first locate the storm center, and then you kind of follow this pathway here to determine what kind of image are you looking at. So if we look at like a satellite image, here there's a satellite image of Typhoon Chanthu in the Western Pacific. This was for the exercise we did. This is the satellite image that they use. It's called the BD curve. This is a special enhancement that's done to the satellite imagery to highlight particular features. And this is what the Dvorak technique uses. It uses this enhancement. And you can see that sometimes that it's not really easy to see the center in a system like this, somewhere underneath this blob of cold thunderstorms. So you locate that center, and then you follow this kind of pathway. Is there a curve band that's associated with the features? Is the system under some wind shear? In other words, are the thunderstorms being pushed away from the center such that the center is exposed? You can actually sometimes see a swirl of clouds exposed completely outside of the thunderstorm activity. Or is there an eye? If there's a clear eye, then you follow this pathway. And so you use these types of pictograms or these paths here to assess the imagery, try to figure out which image best fits within these patterns. And then you get what's called a T number or a tropical number. And you can relate these T numbers, which go, on a scale that I can show. I think I've got the scale up. Maybe I got rid of it here. But in any case, the scale you can see goes up from like about a 4.0 would be a hurricane up to 6.5, and then you can make adjustments. And then you have lower intensity estimates for tropical storms down to like 1.5 or 2.0, whatever. So you can use this to get the intensity, and then there's some adjustments you can make on the side over here for some adjustments if you have a really, really warm eye and really, really cold cloud tops around the eye, like a really, really strong convective ring or something like that. So the key here, though, is that when you do Dvorak, you're not doing it in a vacuum. It's very, very important that the previous estimate you did 24 hours ago has to be used to make the appropriate changes here. And the goal there is we don't want to change the intensity of the storm too fast because we know that a lot of times there's a lag that will occur between the presentation of the satellite image and the intensity. So sometimes the satellite image will look really spectacular, but there can be a little bit of a lag with the intensity. And Dvorak kind of figured that out. And when you get down to the bottom here, you can see there's a couple different models. If nothing you're doing makes sense, you can't really use any of those other methods above, then you can just look at this pictogram here and you can say, well, which one of these images most closely looks like the image that I'm looking at? And from here, you can get these T numbers here, these pattern T numbers, and they go from 1.5 up to a 6.0, so up to category 5 hurricane. And you can actually get higher than that if you make some adjustments. So this is basically the Dvorak technique, and this is what is used worldwide to get the intensity. And as I mentioned, it takes a little bit of time to get good at this because you got to look at a lot of satellite images, and you've got to experience a lot of changes in storms and look at different kinds of structures to kind of understand how the quirks of the technique work. We did an experiment back in 2008. We did a double-blind experiment where we had 5 Dvorak experts, and these are some of the best Dvorak people, that were doing this work at the time. And we had them all do estimates of a couple typhoons out in the Western Pacific. And what was interesting, what we found is that very rarely did they agree. Very rarely did they agree. When we found happens is a lot of times, especially when the pattern is not super clear, like an image like this, where you have just kind of a blob of thunderstorms, there's definitely some banding here and some cold cloud tops, but analysts will find different center locations when it's ambiguous like this. And when you get a different center location, you get a different estimate. So there is information there. It's good to have actually several people doing this, because what you can do then is you can say, well, there's clearly some uncertainty here. There's an ambiguous image that people are struggling with. We can take an average of those. If you take an average of all those values, you get a lot closer to the ground truth. And we actually had aircraft flying in that particular field campaign in 2008, so we could actually validate what the Dvorak experts were looking at. And so one thing we have learned is that the more estimates that you have, the more likely you are to get a good consensus or an ensemble of estimates, and you're probably going to get closer to the truth. And the Hurricane Center does this all the time because they have at least 2 agencies that do this routinely, at the Satellite Analysis Branch and at the Tropical Analysis Forecast Branch and the Hurricane Center. And they have at least those 2 estimates that they can kind of combine together. And like I said, sometimes they don't agree, and the Hurricane Center has to kind of decide which one to go with.
Where does the automated Dvorak technique component fit into this process?
So that's a good question. So obviously we've moved beyond this to some other techniques, and one of the early attempts was, can you automate this? Can you take an algorithm and take a satellite image and do the Dvorak with this automated algorithm. And then that's exactly what a number of people did. Ray Zaire did this with a digital Dvorak technique out of Colorado in Sierra. And then Tim Olernder, my colleague here, and Chris Veldin put together this advanced Dvorak technique that is used quite a bit as well. And so the initial attempts were to basically just duplicate this whole diagram. Take this diagram and try to duplicate this as much as you can. We've since moved beyond that a little bit to some methods that are hold up a little bit better, especially for when the storm is not as well defined. There are, I mentioned there were a couple quirks here. For example, when you look at the eye of the hurricane, I'll bring up a storm with an eye in it just to show you. So here's an image with an eye. On the image on the left was previous image 24 hours ago. The image on the right was the current image. So when you have an eye like this, you're using these cold rings of temperatures around that eye. And there's a question as to which one of these temperatures you use in Dvorak. Do you use this gray shade or do you use the white? So that type of ambiguity is done away with in the advanced techniques, these automated techniques. They just take a mean value of this ring here. And a lot of times that gives a better answer. So if people want to look at these techniques, they can always go to our homepage and actually look at these. Another way to look at them is what we call the satellite consensus. So I'll show that in a second. So this is our tropical page here, where people can go and look at different kinds of satellite imagery, different kind of satellite intensity estimates. And as you mentioned, we have this technique called the advanced Dvorak technique. So this automates the Dvorak method, and I'll just show the case for Darby here. And we can see, here's that image that I was talking about. This is the BD curve, which the Dvorak, the ADT uses. And then you can look at kind of a time series of how the ADT is doing here in the blue. So the blue is what we call the current intensity number. The green numbers here are adjusted numbers. They're a little bit more, they'll fluctuate more because they're not averaged over time. And that's another thing that's important, is that when you look at an image of a tropical cyclone, a lot of times you don't want to look at just one image, one snapshot. You want to look at about a 3-hour animation, because there can be small fluctuations that can be going on in the thunderstorm activity that are not really relevant to changes in the intensity. So looking at those averages and taking averages over a period of time tends to be more skillful than using just a single image. But there is information in the single image. Sometimes when a storm is really rapidly intensifying, that most up-to-date image gives you a little more information as to what's happening with the storm, and the Hurricane Center will use that. So you can see those fluctuations here in the green with the ADT. So that was developed in the 1990s. We had one of the challenges that we had with the ADT is that because you're using infrared satellite imagery, if say this image here on the left of this typhoon, there's no eye there. But if you were to go and look at a microwave image, you can see an eye. You can see eye features and other frequencies, other satellite imagery. And so the challenge was that if the ADT didn't have an eye scene, but the eye was getting going underneath those cold cloud tops, it would get behind and would plateau. So what we did in the last 10 years or so is that we developed a way to use the microwave imagery to combine it with the ADT and provide inputs to the ADT to adjust it upward in the cases when there's an eye that's developing in another type of imagery like this microwave imagery. So it's really become more of a multispectral kind of approach to getting at the intensity, basically using as many of the tools as we can pull into it. And that's also important for the position too, because again, as I said, you might have a big blob of convection. You can't find the center there very easily, but in the microwave, it's clear as day. So this can provide additional information as to the center location too.
Yeah, and just a reminder to folks that may not be all that familiar, your microwave is coming from the polar orbiters, correct?
Right. Yeah, that's correct. Yep.
You're never getting you're not getting the same snapshot every time one makes a pass, which is kind of one of the challenges of that aspect. Do you foresee that capability somewhere in the distant future in a geostationary mode, or is it just too high a resolution requirement to make that?
So there are a couple of ideas about that. So yeah, just to reiterate, yeah. So the imagery I'm showing here, this is geostationary. You can get an image every 30 seconds now from the current satellites. But polar orbiting satellites, we only get an image twice a day. Sometimes it'll even miss the storm because it's a narrow swath. Maybe could be 600 kilometers out to maybe about 1,500 kilometers or so. So one way to accommodate that is just to launch a bunch of these polar orbiting satellites and have them follow each other so that you get an image every couple of hours. But even when we do that, sometimes we miss. So one way to go at that is to launch a swarm of satellites. And so one of the projects I'm on right now is called the Tropics Mission. And the Tropics Mission, the idea there is instead of building these really, really big, expensive satellites and launching just one of them every 10 years or so, why don't we build much smaller satellites and launch a bunch of these little satellites? So actually, I think I have an image up here of that I can show. So this is the Tropics satellite mission here. And you can see these are very small satellites. They're like the size of a loaf of bread. And the idea is that you can launch a bunch of these. In this case, we're launching 6. Though actually we had a problem with our first launch. The two didn't quite reach orbit, so we're working on how to fix that. But you can launch a bunch of these in succession, and they'll follow each other, and you can get images every hour to every hour and a half. So that's one way to get at the problem of polar orbiting satellites not having the temporal frequency of, say, a geostationary satellite. The other idea is, well, why don't you just put microwave instruments on a geostationary satellite? Well, the problem with that is that the geostationary satellites are much further out from the Earth than these polar orbiting satellites, which are orbiting much closer to the Earth. And the challenge there is you need a dish, you need a satellite, you need a receiver antenna sufficient to receive the microwave signal. And if you're too far away, then that presents a challenge. So there are a number of agencies that are working on mitigating that and coming up with innovative ways, kind of like they did with synthetic aperture radar. Coming up with innovative ways to receive that microwave signal on a geostationary satellite. And we'll see if that works. I think there are some test beds that are coming up, some ideas of launching these and testing them out and see how they work. And it's very possible that could improve things.
Cool. Is this CubeSat data going to be available on your website, or you keep that closer to vest until you've proven the technology?
Yeah, so these are some early images actually from that satellite. This is Typhoon Menduli from last year, and we're working on making this data. So this is from the Pathfinder satellite. So prior to launching Tropics, it turned out we had a spare. We had an extra one that we were doing tests on, and we said, well, why don't we just launch that and just use that and just kind of test out the data. So that is actually providing us data right now. In fact, I could go up and I could look at Hurricane Darby right now. There's a bit of a delay in the data. It wasn't designed to give us data and really quickly. There's a delay of about a day or so in order for us to process it because we don't have all the downlink stations. But yes, eventually the idea is that once the satellites are launched, we'll have this data on a website that people would be able to view in near real time or as fast as we can get the data downloaded.
Very interesting. I don't want to hog all the conversation here. Either Tim or Hal, if you have questions or comments at this time, that'd be a good. Why don't you hop right in?
Go ahead, Hal, and then I'll go to the online questions first. But go ahead, Hal.
Yeah, Derrick, I remember when I was at LSU, I was there for about 8 years, and a lot of times we would pull up the CIMMS satellite imagery from University of Wisconsin. It was incredibly high resolution. What's the finest resolution that you have on your satellite imagery that's posted on the web?
We have the highest resolutions, will be from the visible images. So we're down to a half a kilometer on the visible channels, and about a kilometer or so it depends on the sector that we're looking at for the infrared. The microwave channels are much more coarse. So when we look at microwave imagery, we're looking at on the order of a resolution of about 5 kilometers, about at the highest, up to about 50 kilometers resolution. So, the microwave data gives us a really interesting and different view, but there are some issues, related to the resolution of the imagery. So that's why we need I've kind of thrown this up here to kind of show you this idea that we have all these different kinds of satellites and different sources that we can use. And so, yeah, we provide the highest resolution data on the page that we have.
Derrick, you mentioned that the Dvorak technique uses infrared satellite imagery. Do forecasters ever use this really high resolution visible imagery as well to kind of really zoom in and see if shear's happening or anything like that?
Absolutely. In fact, a lot of times the infrared is very difficult to assess the center position. The visible image will show the banding features, especially in the low-level cloud lines, rotating into the center, sometimes much better than the infrared will. And if the visible image is available, the satellite analysts will definitely use the visible image to locate the center relative to those features. There is a Dvorak method for visible imagery, but most people do not use that. They mostly use that infrared imagery, but they do use the visible imagery to locate the center. There's been a discussion in the community over the years, when you do Dvorak, can you use microwave to do Dvorak? Is that cheating? Can you use the visible image to locate the center if you're using infrared? And the answer is you really probably should use all your tools to get that center position, because it's so important to determine the intensity relative to those convective features. So absolutely, they use the visible imagery.
So Derrick, is it possible that someone would use microwave or visible to maybe help locate that center, but then go back to the IR to actually do the measurement once they know that geographic center?
Exactly. That's exact. And I mentioned that field campaign where we did that double blind method, and it was interesting because different analysts did that differently. Those who used the microwave imagery to get the storm position tended to do better, because the Dvorak is very sensitive to the position of the storm relative to the convective features. So using the microwave to kind of hone in on where the center is will definitely result in a better estimate.
Thanks, Derrick.
Yep.
We got a question coming in online from Casper, and I'll just read the question. It's easier that way. He says, what parameters do you use to determine the distance of the diurnal cycle from the center of the circulation for tropical cyclones on the TC diurnal tab?
What do we use to determine the distances? Was the question?
The distance of the diurnal cycle from the center of circulation for tropical cyclones on the diurnal tab.
Yeah. So that's Jason Dunyon's work. He's done some really cool work with trying to assess these diurnal changes that we clearly see in these storms. And so he, on that particular page, I think has a couple fixed values. I think 100 kilometers, 200 kilometers, 300 kilometers, and 400 kilometers. And I believe it's an annulus that he uses, so kind of a ring around that area, and then looks at the changes in the temperature at those distances. So they're distinct distances at 100 kilometers, 200 kilometers, et cetera. So looking at how the temperature of the cloud tops are changing over time at those distinct rings. And then what he can do is he can plot out how those changes are occurring over time. And what that does is it shows you that we often see these pulses of convective bursts that move outward from the tropical cyclone center associated with the diurnal cycle. And a lot of time it's really very remarkable. You can just see when he does these differences between images over a period of a few hours, you can see these rings of convection basically blowing outward from the storm. And as I mentioned, Dvorak saw this and saw these changes and saw that they didn't really affect the intensity at all, despite the fact that you think that they would. If the convective signature is relevant to the intensity, then why isn't this affecting things? And the answer we think is that a lot of this is happening at the very top of the storm, and that information or the impact is not making it down to the surface where the intensity is measured. So I think the answer to the question is that we do that at distinct distances on that particular product at 100, 200, 300, and 400, I think.
Maybe I'll let this go back to Bill, but one of the things you've done a lot of work on is Eyewall replacement cycle, timing the timing that and stuff. And Bill, I don't know if you want to lead that discussion as we head into that, because I think it's fascinating. So this has been one of the things you've really focused on, isn't it?
Yes. So one of the challenges we have is that storms undergo what you just said, these eyewall replacement cycles. And what happens here is that you have an eye in the tropical cyclone, and then convective bands will rotate around that eye. And in between those bands will actually be what we call a moat. It's very much like a moat, in a castle, and that there's a lack of thunderstorms. And it's actually, there can be a little bit of drying that can go on in there. We can actually see that in the aircraft data. But eventually that ring, that outer ring of convection, will rotate around the inner eye and enclose it. So here's an example. This is a pretty classic example from Hurricane Ivan, what I'm showing here. You can really see this best in the microwave channels. It's very difficult to see this in geostationary imagery. The microwave is looking at an ice scattering signal. It's looking through the cloud top. So even though cirrus clouds could cover the top of the storm, the microwave is transparent to all that, and we can actually see these structures through the clouds. And so this is a very useful tool for monitoring eyewall replacement cycles. So this is Hurricane Ivan from 2004 undergoing an eyewall replacement cycle in the microwave. And you can very clearly see as the image starts, we have an inner eye, we get another outer eye that wraps around that. And then what happens is that this will choke off the inflow to that inner eye, and the inner eye will weaken and dissipate. And then the outer eyewall will contract inward. And it's possible that this entire process could start again within 24 hours. In fact, Ivan had 4 or 5 of these eyewall replacement cycles, so quite a few of these. What happens during this process is that when the inner eyewall weakens, the storm weakens oftentimes. And because that weakening is as not represented in some of the intensity estimates, Dvorak is a good example of that. These storms will undergo a fluctuation in intensity where the intensity will dip and then intensify again after this process completes. But Dvorak will just be flat. It'll just be a flat line through this whole process. And so it won't represent these intensity changes. And these intensity changes are important because we've made a lot of progress in forecasting where hurricanes will go. We've made tremendous progress on track forecasts, primarily through computer modeling. We've made a little bit less progress in forecasting intensity changes. And these eyewall replacement cycles are one of the challenging forecast problems because this is happening in an environment that's very favorable for intensification. So all of our guidance will say, well, this storm is going to intensify, but the eyewall replacement cycle will stop that process and the storm will actually weaken for a period of time. And you can end up with a forecast bust a little bit. Maybe you're going for a category 5 and you end up with a category 3. Well, you're off by 2 categories. So these types of intensity fluctuations are important to monitor. So we use this microwave to monitor them, but we also are starting to develop some tools to actually forecast when this process will happen. I can actually show an example of that in our current storm in Darby. So we have a product called MPERC, which is a microwave probability of eyewall replacement cycles. Another way to look at the microwave imagery is to look at it over a period of time in what's called a Hofmolar. So this is time here increasing as we go downward. And this is the microwave signal of these microwave features going out to 200 kilometers. And we can just kind of see how these microwave features kind of change over time. And from that information, we can actually build a model to predict when an eyewall replacement cycle will happen. So this isn't using a weather model. This is actually using satellite imagery to predict how these changes will occur. And we can produce probabilities of an eyewall replacement cycle from this product. So the Hurricane Center can use this and say, well, we're forecasting intensification, but this model is showing that that intensification process could be interrupted by the eyewall replacement cycle, and therefore we might have to adjust our forecast accordingly. Very challenging, especially if the storm is approaching coast.
Yeah, what are the typical probabilities in that type of a technique? What are you looking for as for a window where you start paying attention to it?
Yeah, that's a good question, because this process can take about 24, 36, or even sometimes 48 hours in advance. The goal is to try and give the forecasters advance notice. So what we have found with this technique is that for storms where we have these probabilities that approach, close to 100%, very high probability of an event occurring, those tend to be the most disruptive events. Those tend to be the type of eyewall replacement cycle events that will definitely weaken the storm. And the other things that we found is that the stronger the storm is, the more likely it is for this process to weaken the storm. What we find with weaker storms that are kind of on the lower end of the intensity scale, say 80 knots, 85 knots or so, those storms might undergo an eyewall replacement cycle, but it's just a blip. It might just be like 6 hours of steady state. So it's undergoing rapid intensification, it pauses for 6 hours, and then the rapid intensification resumes. So we see that for the weaker storms, but for the really strong storms, these category 4s, category 5s, if they undergo one of these structure changes like an eyewall replacement cycle, it tends to be much more disruptive. And these probabilities will give some guidance as to that. You can see there was a lower probability here for Darby on the order of about 25, 30, 40% or so. And it did go through a weak ERC, but it didn't seem to be terribly disruptive for Darby at that time. But these really, really higher probabilities, when we see them bump up higher, those tend to be the more disruptive ones.
That's cool. When you have those animations, the mimic in there, can you tell us a little bit about how you make it look like a continuous image? What kind of algorithm do you have to use to produce that? Yeah,
so Tony Wimmers worked on this a number of years ago. It was pretty cool because as we mentioned earlier in this discussion, these microwave images only come over a storm twice a day. And so how can you make an animation from just 2 images a day? Well, we have multiple satellites. We might have gaps on the order of a few hours. And what you can do is if you know what the winds are in the storm, you can actually take those satellite features and advect them or rotate them in time based on the wind flow. And if you put those all together and do like an hourly resolution of that, what we call a morphing technique. So this is just morphing the imagery over time. It creates this product that looks like a radar. Looks like a radar animation. And that's was kind of the goal of it. So there are some artifacts in here, and the rotation features are rotating based on the intensity. It's not based on necessarily completely on the intensity determined from the imagery, but it really is a very useful tool for monitoring the time changes in these features. I'll mention a funny anecdote. So funny story is, sometimes with this morphing technique, it's just an algorithm, and sometimes there'll be glitches, and you can actually see some glitches here. You can see some weird lines in here that clearly are not real features. You can see some artifacts, and inevitably we get an email from someone saying that's HARP. So for those of you who aren't familiar with what HARP is, or chemtrails, yeah, we'll get an email from someone saying, "Look, someone's trying to modify this hurricane." No, it's just an animation glitch. It's not. No one's messing with the hurricanes. Of course, someone will write you on that image you're showing there and say, "How come Grand Cayman's moving?" This is the storm. Some people fail to recognize that it's a storm-centric mapping technique. So yes, exactly. Storm-centric images just to make the animation look a little cleaner. Yeah, exactly. Yeah. You can really tell from that. In hindsight, looking at that, you could the power of the Eyewall on that side as it went across that's one of the worst damage events Grand Cayman's experienced. Right, and that's why this work is fairly important, because when these Eyewall replacement cycles occur, what happens is that the strongest winds shift from the center out to a larger radius, and that's a very fundamental change in the damage area that this storm will represent. And so being able to try and estimate when that will happen is very important. It's very important because it impacts storm surge as well. So not only does it impact the radius at which the damaging winds are occurring, which is important for the warning process for the winds, it also changes the structure of the storm such that it's more conducive to produce higher storm surge. Yeah. We saw that with Hurricane Katrina as it approached the Gulf Coast, underwent an Eyewall replacement cycle at Category 5 intensity and was weakening as it approached the coast, but the storm was larger and those winds had shifted outward to a larger radius, and you're just pushing more water with that wind field and increase the storm surge threat. Yeah, that energy doesn't go away. No. Someone sent me a question about verification, the satellite consensus technique in there. What's your estimate of skill at doing that now? Right. So I've done this slide back up just because I think it's illustrative of what we're trying to do here, where we have all these different sources of information for intensity. And we talked about Dvorak. We talked about the advanced Dvorak technique. We've talked about some microwave techniques. We can actually estimate intensity of storms from the microwave. We can use a couple different microwave channels. We can use these ice scattering channels that some people might be familiar with. We also have what are called microwave sounders. That's what the Tropics Mission is a microwave sounder. We have synthetic aperture radar. We have the SMAP system. We have a number of these systems that produce intensity. And we can combine all of those into a single estimate into what we call a satellite consensus. But the question is, well, how do you verify that? Predominantly, it's aircraft data. So most of our verification is in the Atlantic or the Eastern Pacific, where we fly aircraft that can fly out into the storm and actually determine which one of these answers is the best answer or which one of these methods is best. So aircraft data, by and large, is what we use for validation. Either using the flight level data, we typically will use the best track. So the Hurricane Center will take all this information, including the aircraft data, and come up with what's called their best estimate of what the intensity is. And if we do our training and validation on the data sets that contain the aircraft data, it tends to have the highest fidelity, tends to be the best answer. We could do it on global data. We can verify against best tracks in the Western Pacific or the Indian Ocean, but those are predominantly made up of the Dvorak technique. So we're really just going to end up verifying against the Dvorak technique, which has a lot more uncertainty, as we've talked about. Now, I will say, occasionally we do get aircraft data out in the Western Pacific. We've flown some missions out there. The Japanese are doing some research missions. Taiwan has an aircraft program. Sometimes they fly into the core of a storm and get us some good data. Or sometimes a storm actually passes over an island. The Ryukyu Islands are a really good example. You have more tropical cyclones in the Western Pacific than you do any part of the world. And a lot of those islands do get hit, and we do get observations. Usually when we do that, we look at the pressure observation. It's just a better estimate of the intensity. It's unlikely that an island station is going to experience the strongest winds in a tropical cyclone. So when we do validation of these techniques, we can validate either the wind estimates or we can validate the pressure estimates. So if we get observations out there and at these island stations, then we'll validate the pressure.
Interesting. Before I forget, as our time is running close here, though, one topic I don't think we've talked to very much is the AI aspect of your work. Where do you see that going?
Yeah, that's a really good point. And yeah, we probably could have spent an entire talk on that. So exactly. So here's the thing: is that a human eye can look at a satellite image and get an estimate of the intensity. You can actually do that with what we call computer vision. A computer algorithm can actually look at an image. And if you have enough of these images, and when we say enough, we're talking like thousands and thousands and thousands of images, you can put these into these deep learning models, and the model will sort out which features in the image are relevant for the intensity. And so there are a number of methods that are underway right now to leverage this deep learning tool basket that we have to take various types of satellite imagery and get an intensity estimate. And those methods are using both the infrared imagery here. So here I'm showing an infrared image and some features from an objective deep learning technique. We can also do this with microwave imagery as well. We can take the microwave imagery either from the 85 gigahertz ice scattering signal or the 37 gigahertz water vapor signal, and train a model to look at that image and produce an estimate of the intensity. So there are a couple of these deep learning techniques that are actually, we just posted them up on our page in the last several weeks as going live to kind of augment the other suite of intensity estimates that we have. And I think you're going to just see more and more of this. These methods are starting to become very, very skillful, on the order of as skillful as the Dvorak technique, which is kind of a benchmark that we use. In some cases, even better. Hopefully, if anyone's learned anything from this discussion, it's that the more sources we have, the better, because some of these storms aren't classic-looking storms. I mean, Hurricane Sandy certainly wasn't classic off the east coast of the United States. So having lots of tools that can kind of analyze the storm, especially when the storm is not classical, or if there's some ambiguity in it, are definitely helpful. So these tools are all coming online. They're being kind of thrown into the hopper of all the other methods that the Hurricane Center has to look at, and they'll be evaluating those over this upcoming hurricane season.
Great. Yeah. That leads to another point about the practical reason that consensus type forecasting is very useful. It's all on the crunch of time you have on the 6-hour forecast cycle. You really have to, you can't possibly look at all this information now that's streaming into your workstation. And
right.
Being able to come up with tools to bring all of that to bear on an answer is great.
Yeah, exactly. And, we provide those via our page where people can look at them. The Hurricane Center has access to this. So this is one of the deep learning tools here called the Deep Multinet. You can click on that. This is the current Deep Multinet intensity estimates for Darby that you can see. And then there's imagery associated with that. And then we also have a infrared version of that to look at the infrared imagery, and a version that actually combines the two of these into one. The other area that we're really focusing on with deep learning right now is rapid intensification changes. And so another tool that we've developed, Sarah Griffin in our group has been working on this with Tony Wimmers to use satellite imagery and some other environmental factors such as wind shear, SSTs, moisture, things like that, to try and estimate the probability of rapid intensity change. I can show that one real quick here too, if I go to it. So this is a rapid intensification model that's used along with some of the standard tools we have. One of them is CIMMS, has a rapid intensification model. It's a statistical tool. And just trying to look at areas where one of the biggest challenges in forecasting in tropical cyclones is forecasting these rapid changes in intensity. We don't do a very good job of that. And so working on trying to solve that a little bit.
Great. Well, we could go on all day. Tim, I think I'm going to turn it back over to Tim here because we're running towards the end of the hour there. Catch any more questions you have and aspects that you might want to follow up on, Tim?
No, we are getting close, and you guys are amazing because as the questions come in, you're answering them before I get to ask them. So you're all watching the right places. So we appreciate that. We really appreciate what you guys do and the website. There's so much information there. It's our go-to website for watching the dust coming off of Africa.
Oh yeah.
Yep. So we appreciate that, and thank you for all the work you do. Hal, let me give you a chance to throw some final thoughts in there if you have something.
Yeah, a great presentation, Derek. Very last atmospheric physics question. These convective diurnal pulses, are they maximizing like in the afternoon with the convective maximum, or is it after midnight when the surrounding environment is colder?
Yeah, it depends on at what radius you look at. And that's one of the things that Jason has looked at is that a lot of times you'll see them start at convective max in the core, but then as convective max starts to wane, those pulses will propagate outward over time. So, a couple of hours after the convective max is when you start to see these changes in the brightness temperatures at a radius, increasing radius moving outward. There is some indication that there are some things that it's possible that these waves, these features might excite some banding features in the outer edges. And so there's still a lot of work going on to try and understand what physically is happening there and how is it may not be changing the intensity, but it might be changing some aspect of the storm that's important. I really think he's right on the cusp of something really important here, and I'm hoping that he'll be able to figure it out.
Thank you, Derek. Great presentation.
Thank you.
Good stuff. Bill, any final thoughts before we wrap it up?
And I've got a lot of learning to do off that site. New stuff comes out this year that I haven't looked at yet.
I've been doing screenshots of so much today just to grab it and go back and look at it later. So,
well, if anybody has questions, hit me up on email. You know how to find me.
Terrific. Thank you, Derek. Great program today. Really appreciate it. And great questions, Bill and Hal. Really, really good stuff. And I hope people go back and view this later. And thanks to everybody online who's been asking questions. Hey, I even got a question about my Cabo pictures, so it's been a good day. So we appreciate that. As always, want to thank our sponsors who make this program a possibility. USAA, South Padre Island Convention and Visitors Bureau, the Weather Company, Weather Boy, the City of Brownsville, the Port of Brownsville, Black Magic Design, Walmart, all a part of this program, many for a very long time from the very beginning at the National Tropical Weather Conference in South Padre Island. We will be back live on South Padre Island in April once again, so we encourage you to join us. Watch here for registration information for that. That wraps it up for today. For Bill, Hal, Derek, and the whole group, and especially for Alex Garcia, thanks for joining us. We'll see you again next week when our guest will be Jeff Masters, who's going to talk about the Gulf of Mexico Loop Current. See you next Wednesday at 10 a.m.